So in today's lesson, we are back to connected particles. We've moved on to pulleys, but we're going to make one change. Previously, we looked at pulleys where although the bodies are moving in different directions, they were both still moving vertically. What if we used a pulley to have one body move vertically and one move horizontally? So this is like us having a box on a table which is connected to another box which is hanging vertically, and to change the direction of the string, we've passed it over a smooth pulley. So this is a combination of a few things we've seen. We've seen vertical connected particles and we've seen horizontal connected particles. Now we're taking one of each and combining them. As always, we need to think about the forces that are acting on the bodies in question. The natural place to start is going to be with the weight. So let's say we have a 6 kilogram box here and we've got a 4 kilogram box here. The reaction force for the hanging weight is going to be tension. The reaction force is in the string. The reaction force for the 4 kilogram weight is going to be a contact reaction force, just the natural reaction force that comes from a body being in contact with a surface. There is a more subtle difference to the two of these. Yes, they both have weight and reaction forces, but for one of them, the weight is the driving force. For the other, the weight is not the driving force. For the hanging body, the 6G is the driving force. The weight is what's going to cause this body to move. For the one that's on the table, however, the weight isn't going to make it move. The driving force in this case is actually the tension in the string. Now, depending on the scenario, we may or may not have resistive forces, friction, etc. that are also at play. What's interesting to see here is that we're not going to make use of the weight or the contact reaction force in our calculations, because for motion equations, we only need to consider the forces that are in the direction of motion. The forces we're going to consider for the 4 kilogram mass are tension and the 2 Newton resistive force. Okay, we're going to do what we usually do. We're going to concentrate on one object at a time. So, ready to use Newton's second law. For the 6 kilogram mass, it's going to be 6G minus T equals 6 multiplied by A. For the 4 kilogram mass, it's going to be tension minus 2 newtons equals 4A. As we always do, we can add together the left-hand sides and add together the right-hand sides. And that gives us 6G minus 2 equals 10A, and just rearranging, we can get an answer for the acceleration. In this case, we can't really leave it in terms of G. This looks a little bit cumbersome, so we will put this into our calculator, and we get 5.68 meters per second squared, and that is to 3 significant figures. Once we have the acceleration, we're going to substitute that to find the tension. T minus 2 equals 4 times 5.68. We could use the more accurate version, which is the fraction containing G, but in this case, we had an exact answer to 3 significant figures. Either way, we get tension of 24.7 newtons. So just as before, we are finding an unknown acceleration and an unknown tension. Because we have a smooth pulley, we know tension is the same all the way through the string on both sides of the pulley. And because we have an inextensible string, we know that the velocities and the acceleration in the particles, in the masses, are going to be the same all the way through the journey. Okay, as always, if we've found acceleration, we recognize that this is the key to moving into constant acceleration problems. This opens up the world of SUVAT. What if we wanted to know a little bit more about these masses as they move around? Let's say that there are 10 meters from where the hanging particle is until the ground. Can we find the velocity with which it hits the ground? Okay, collecting SUVAT variables, displacement is 10, initial is 0. We're looking for this velocity. The acceleration we found to be 5.68. If we go for v squared equals u squared plus 2as and substitute our values in, we get that v squared is going to equal 113.6. If that's v squared, we're square rooting to get a velocity of 10.7. 10.7 meters per second is the velocity that this particle will hit the ground. And just like we've looked at before, if that's the velocity when it hits the ground, that is the projection velocity of the particle on the table. The system is going to be broken, the string will no longer be taut, but then we just have a basic horizontal projection question from then onwards. So the key to link a motion equation to constant acceleration formula use is the acceleration. Acceleration is massively important here. Once more, let's think about the forces acting on the pulley. If we focus in on the pulley, there are only two forces in contact with it. Both of these be in tension, but now they're both moving in different directions. Last time round, they were both going down. Now we have one off to the left and one going down. What would be the magnitude of the force acting on the pulley? What direction is this force acting in? So just focusing on the pulley, we've drawn the tensions going away from the pulley. If we write that in vector form, it's negative t, negative t. We found a value for tension, so we can actually write that in. It's negative 24.7, negative 24.7. Okay, let's actually draw the resultant vector diagram for this. So this is our starting point. We're going to the left by 24.7. We're going down by 24.7. The magnitude of this force acting on the pulley, we can find that by using Pythagoras. We've turned this into a standard, straightforward vectors question. What is the magnitude of this vector? The magnitude, and that comes from squaring 24.7 and adding it on. Okay, when we calculate that, we get 34.9 newtons. Well, what if we wanted to know the direction that it's moving? This is a recognizable type of triangle. Both the perpendicular lengths are the same. This is an isosceles triangle that has a right angle. So that means the other two angles must both be 45 degrees. So actually, if we're asked about the direction and the magnitude of the force acting on the pulley, this is exactly what we do, and we're using Pythagoras in the first instance. We could use trigonometry, but actually I'm demonstrating some intuition, some insight to the diagram in front of me. Isosceles triangle, this is 45 degrees. Just about finished. But before you move on to some practice questions, let's take a quick look at the specification and exactly what it is that students are expected to be able to show. Exactly what the examiners are anticipating you'll be confident in. While you read through, I want to quickly remind you that it will be sensible for you to come back and watch this video, re-watch this video at a later date. Maybe come back in 2 or 3 weeks or just before an assessment. And as you watch through that second time round, because you've done your practice, a lot of what you go through here should resonate with you much more, and you have a chance to really embed your understanding of the difficult concepts, the ones that I've been flagging up as A star through the video.